Hello. In this video, I would like to solve an hard example on inverse function. Let f, of course, difficulty is a subjective thing, so it is assumed to be difficult. Let's see how you feel about it. F is a function from R to R and defined as absolute value x times absolute value x plus 1. And these are the tasks that we need to perform. We need to find all intervals in R such that f is 1 to 1. And the domain, we need to find the domain of f inverse, find then definitions of f inverse, decide whether f inverse is continuous, and decide whether f inverse is differentiable. So what we need in this question, we need to see, in order to be able to find the subintervals of R, where f is increasing or decreasing, that will give us the one-to-one parts or subintervals, that the f will be one-to-one in those subintervals. So we need to look at the sign of f in order to be able to see where f is decreasing or increasing. That means we need to find the zeros of derivative of f and the singularities we need to look at as well, if any exist. First, recall ourselves what was the definition of the derivative of an absolute function, that is x divided by absolute value of x. So we want to take a derivative of our function that is absolute value of x times absolute value of x plus 1. So we have a product here. We need to apply the product rule. Derivative of the absolute value x is x over absolute value x times x plus 1 absolute value of x plus 1 plus now this and the derivative of this and the derivative of this will be x plus 1 divided by absolute value of x plus 1. Now the next task that I am doing is making the denominator is 1. So I'm multiplying this part with the x plus 1, and I'm multiplying this rational number with the absolute value of x. Then I have x plus 1 squared plus x squared x plus 1. These are squares. Absolute value would disappear in this case. I will have x squared plus 2x plus 1, and I will have x squared x plus 1. X is a common here, x is common here. I'm taking the common x out. What I have left here, x squared plus 2x plus 1 plus x squared plus x. So I have 2x squared plus 3x plus 1. So I have a polynomial in the denominator, and I have multiplications of the absolute function in the denominator. So it's a rational function. So the zeros of the f prime is coming from the here. That is 0 will make f prime is 0, and minus 1 will make it this one 0, and 2x plus 1 give us the minus 1 over 2 makes the f prime x is equal to 0. And the singularity is x is equal to 0 and x is equal to minus 1 is the singularities for the derivative of f. Okay, now these are the critical points, and that will help us to figure out what is the sign of the f prime that will give us where the function is increasing and decreasing. So the x, we have minus infinity, minus 1 over 2, minus 1, minus 1 over 2, 0, and infinite. And x plus 1 will be negative up to minus 1 and positive afterwards. So 2x plus 1 will be negative up to minus 1 over 2 and positive afterwards. And then if you multiply these three, so you have a negative, negative, negative. So positive, negative, that is negative. So I'm multiplying these three polynomials here. And then you have negative, positive, negative. So that will give us the positive. You have negative, positive, positive will give us negative. Then we have positive, 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 that will give us positive. So the sign of f prime is determined by this polynomial, because in the denominator you have an absolute value, it is always positive. So the sign is exactly, sign of f prime is exactly this row. That's minus, plus, minus, plus. That is, f will decrease in this interval, increase in this interval, decrease in this interval, increase in this interval. Now let's have a look what are the function values at that time. If we have f minus 1, we have 0. If you put f is 0, we get 0. If you put f minus 1 over 2, you get 1 over 4. So these are the points these are minus 1, 0, minus 1 over 2, 1 over 4, 0, 0 are the points that the function, the graph, passes through. Okay, now then we have in x-axis we have minus 1, minus 1 over 2, and 0 are the critical points. And then it says the function goes down up to to minus 1 and minus 1, 0 point, and then goes up to minus 1 over 2, 1 over 4. I assume that this is like a minus 1 over 4, 1 over 2, 1 over 4 point there. And then you go down, and that is a decreasing, and then increasing. That's an increasing. Now, this part looks like a tip, this, because it's a cusp form. Why? Because f inverse has a singularity at x is equal to minus 1. So this is a singular point, so it will look like a cusp. And here as well, we have a cusp there. At x is equal to 0, we have a singularities. Okay, so that is the graph of the function. So what are the intervals? So this is the first interval. I call it I1, minus infinity to minus 1. In this interval, of course, f is 1 to 1. Up to here, up to this point, f is also 1 to 1. That is I2, from minus 1 to the minus 1 over 2. From I3, from here to here, minus 1 over 2, 0. That's another interval that the function will be 1 to 1. And then this function here will be from 0 to infinity, and the function is also 1 to 1. So f inverse exists whenever f is 1 to 1, which are on these intervals. If you think about this is, since we have a different intervals, let's call them f1 from I1 to R, defined exactly the same definition. The function, I am not changing the function, I'm just changing, so this is a function all the time, but I'm giving the name f1, f2, f3 with respect to the domains of that function. And for the domain of f1 inverse, since this is an interval, that will give us the 0 to infinity. It is easy to see that from the graph, right? This is that is the first interval that we are thinking, and then y will go from 0 to infinity. If we think of this one is domain and this one will be the range, and so on and so forth. F2 will be I2 minus 1 to the minus 1 over 2. So in this range, x, y will be from 0 to 1 over 4, 0 to 1 over 4. I3 minus 1 over 2 to 0, that will give us again 0 to 1 over 4. And then for I4 will give us from the 0 to infinity. That is the increasing part. All of them are continuous because you have a polynomials. So you have polynomials in the denominator, you have a polynomials in the denominator. The F1, F2, F4 are all continuous because they are polynomials. Since the singularities of the derivative of f are 0 and minus 1, f is not differentiable at those points. So f1 and f2 is not differentiable at x is equal to 1, and f3 and f4 is not differentiable at x is equal to 0, and f4 is not differentiable at x is equal to 0 as well. That is the solution of this question. That's all I want to say for this question. Thank you very much.